Okay, welcome back, Math 352. We're getting near the end of the course now, and one of the last things we're going to look at is another case of quadratic programming, but today, instead of looking at the kind of simple-ish equality-constrained one, we're going to move into the realms of a more difficult problem, and that is inequality-constrained quadratic programming. Okay, so it's minimizing a quadratic objective, but this time it's going to be subject to a number of inequality constraints, instead of just equality constraints. Okay, so to start with, we're just going to take a bit of a closer look at our optimality conditions for equality-constrained QP first, because we're going to need to make use of this information when we develop our IQP algorithm. Okay, so if you remember, to solve an EQP, and we'll look at the case with positive definite P, we have the optimality conditions Okay, so these are the KKT conditions that we had last time, and they were that AX star equals B, and PX star plus Q plus A transpose nu star equals 0. Okay, and if we can solve those two equations, and we can write that in matrix form and do that quite straightforwardly, then we've found our optimum for the equality-constrained quadratic program. Okay, so I'll just write the second one in a slightly different way. I'll just write this more generally as f of x star plus A transpose nu star equals 0. Okay, and last lecture I basically stated this result here without proof. So we're going to take a bit of a closer look at this one today and show that it does actually work. Okay, so and we're going to get back into the realms of shadow prices and Lagrange multipliers again. So constraint perturbation. Okay, so we're going to get there in just the same way as we did with linear programming. We're going to look at what happens if we perturb our constraints by a small amount. Okay, now it won't be immediately obvious that we're doing that, but that's what's going to end up happening. Okay, so remember with LP, when we're talking about shadow prices, we're looking at how much does the objective change if we increase the right-hand side of one of our constraints. Okay, so let's start with the statement. If x star is to minimize our function, I'm just writing f of x instead of writing out the whole x transpose px plus qx plus whatever. So I'm just going to write f of x to make it shorter over our constraints. So I'm just dealing with the equality constraint case for now. Then the gradient of f at x star must be orthogonal to the null space of A. Okay, now why on earth is that? Let's have a look. Okay, so we'll prove it. Shouldn't take too long. So we'll assume the contrary. I.e., grad f is not orthogonal to null space of A. Okay, so if it's not orthogonal to the null space of our matrix A, then we can choose a vector in that null space such that a gradient, okay, if we take the directional derivative, then up to a scale factor, it's this here, is negative. Okay, so all that is basically doing is taking the directional derivative of our function in the direction p, and you need to scale it to get the actual derivative, that doesn't matter. The point being, we can choose a p such that this quantity here, approximately the directional derivative, is negative. Okay, but then since So if we move in that direction by some amount, p, that just equals ax plus t ap. Now p is in the null space, so that's just 0, so it's ax, which equals b. Okay, so ap equals 0 for any t that means basically that we can move along this direction, maintaining feasibility, but with our objective dropping. Along p from x star lowering f, which implies x star is not a minimizer. Okay, because we can maintain feasibility and move away from it, and which gives us our contradiction. Okay, so we've got the result that the gradient of our objective function f at an optimum must be orthogonal to the null space of this matrix A from our constraints. Okay, so let's just see what we can do with this. It's useful. Therefore, the gradient is orthogonal to the null space. Let's use the right notation. So that means it's an element of the perpendicular subspace. And if you remember from earlier, it's in the range or the column space of A transpose. Okay, just remember from what we did earlier in the course, these two subspaces are equivalent. Okay, so if grad f of x star is in the range of A transpose, it means it can be written as a linear combination of its columns. So we write that grad f x star equals negative A transpose nu for some nu in Rm. Okay, and that, in fact, is just the condition that we had from the previous lecture. See, that's just that one there. So this just comes quite naturally from this proof that the gradient is orthogonal to the null space of the matrix. It means that we can't move down while maintaining feasibility. And that's where this optimality condition comes from. Okay, so we've kind of proved that optimality condition, but we're going to go a bit further. If we make a small perturbation, delta x to x star. Okay, so we're seeing what happens if we move away. Then we have a of x plus delta x equals ax plus a delta x, and we'll call the quantity a delta x, x star, delta b. So if we make that perturbation, then the corresponding first order, okay, so it's like the linear approximation, change to f is delta f. Well, we just multiply the gradient by the delta x. And it's more convenient to write it this way around, but we could write it as grad f delta x as well if we wanted. It's just a scalar. And putting that together, we know that delta f is equal to negative A transpose nu. Okay, but we know that A delta x is just equal to delta B. So I'll write delta F again. Delta F equals negative delta B transpose nu. Okay, so the change in F is, so you can think of this as in a slightly different way. If you can think of it as increasing the right hand side B by delta B, and it tells me that delta F changes by an amount weighted by these Lagrange multipliers. So just as in linear programming, the Lagrange multipliers are taking on the role of these shadow prices. They tell us how much for a small change in our right hand side our objective is going to change. Okay, so this is obviously to first order. And yeah, so note the difference between this and linear programming. Our function is actually quadratic. This is just the linear approximation of the change to f. Okay, so for a small delta b that's perfectly adequate. For a larger one, it's not. Okay, so we're just looking at basically a slope or a gradient at the optimum. Okay, so therefore Lagrange multipliers or shadow prices again relate increments in the right hand sides of constraints to corresponding changes in the objective. Okay, so that's quite nice. We've got the same interpretation that we can take of what our Lagrange multipliers mean for these quadratic programs, in fact any of these optimization problems we look at, as with what we looked at in linear programming. Okay, so I think that's probably all we need to do about this part right now. So we've understood now where the optimality conditions that I stated without proof last lecture came from, and we've kind of refreshed our memory and verified that our interpretation of Lagrange multipliers is also valid for QPs as well as for LPs. Okay, so let's move on to what our main topic is for today, and that is inequality-constrained quadratic programs. So let's just rearrange this file slightly. I'll put this block of text over here so we can have it all on one page. That's a bit better. Okay, so what we're going to look at next is inequality-constrained QP. Okay, so this is quite a lot harder, and we end up having to develop an algorithm that's a little bit like the simplex algorithm that we looked at for linear programming. But first, before we can actually start solving the thing, we need to define what it is. So consider the following optimization problem. Minimize 1/2 x transpose px plus q transpose x. Once again, you could put an extra constant on there if you wanted to, but it makes no difference to the minimizer, subject to ax is now less than or equal to b. Okay, so we're only going to look at cases where p is positive definite. And we'll see why we need that soon. Okay, and A is an n by n constraint matrix. Okay, so one approach to this problem, okay, it's not the only way, is to use what we call an active set strategy. Okay, and how do we sort of think of this? Well, if we're minimizing a quadratic function subject to those constraints, then we've got a few different things that can occur. So, for example, if we minimize this, and if we minimize this and we found its minimum without just ignoring the constraints for now, if we just minimize the objective, then our objective minimizer, x star, might fall right smack bang in the middle of our feasible region. Okay, and in which case these constraints will be satisfied automatically, and none of them would actually play any part in minimizing this at all. So it could be that none of these constraints are actually active at our optimum, or it could be that a number of them are. So we've got if we're minimizing something and we find that the minimum occurs on the boundary of our feasible region, then some number of constraints are going to be active, and we need to minimize its subject only to the ones that are active. Okay, so if we've got one of those boundary cases where our minimum occurs on one or more of these constraint boundaries, then what we need to solve is really an equality-constrained QP with only the active constraints. Okay, so we'll have a few AI x's equals bi's. Okay, a few equality constraints corresponding to the active inequalities. Okay, and we have to find out which set of equalities or inequalities is active. Okay, at the optimum. So an active set S is the set of constraints that hold with equality. Okay, i.e. a binding or sharp. If we know the optimal active set, which we'll call S star, then solving the EQP minimize over x, 1/2, same objective as before, subject to AI transpose x equals bi for only the constraints that are in our optimal active set, yields the optimizer or minimizer. Of the IQP. Okay, so basically solving an inequality-constrained QP boils down to two things if we're going about it this way. Finding the optimal set of constraints that are active, and then solving an EQP, which we now know how to do. Okay, so there's two problems. This is just like the simplex method, well, not just like it, but quite similar to the simplex method for LP, where we're trying to find the optimal basis, which is like finding the intersection of a number of constraints as well. So, first thing we need to know, how do we know if we have S star? Okay, so before we can go about trying to find this thing, we need some kind of test to tell us whether we've got the optimal active set or not. Okay, how do we know? So let's just continue on. We can identify when we have S star, because first off, the optimizer is feasible. Okay, so it's in the feasible region where F is the set of all points that satisfy inequalities. Okay, so there's no point, no good pulling out some constraints, finding the optimum of that equality constrained, or finding the optimum of that EQP, and discovering that its optimum doesn't actually lie in our overall feasible region. So that's the first thing that has to be true. Second thing, less obvious, but it will become more obvious soon. The Lagrange multipliers are greater than or equal to 0, where nu star is the set of Lagrange multipliers for the equality constraints. AI transpose X equals BI for I and S star. Okay, so when we solve the EQP, if we use the KKT method, then we'll get this set of Lagrange multipliers as well as the X star. And the two things we need to test is that X star is feasible and that nu star is greater than or equal to 0 for all of the Lagrange multipliers. Okay, so how do we make sense of number 2 there? To C2, we're going to look at our perturbation method again. Consider perturbing X star by delta X. And what we're going to see is we can see if we can go, we'll see if we can increase our function, decrease our objective while remaining feasible. If we can, then we're not optimal, and we'll show that whether or not we can do that depends on the sign of these Lagrange multipliers. So just from the result we had before, the corresponding change in f is equal to negative delta x transpose. So let's just see what we had before. Okay, we'll take this form here. Negative delta x transpose A transpose nu. Okay, and I'll write that matrix multiplication out as a sum, because a lot of the news are going to be, we're only looking at a certain set of the constraints. Negative delta x transpose times the sum. Okay, we're only looking at the relevant columns of A from our active set, AI, VI star. Okay, which is equal to, like we said before, the right hand sides times Lagrange multipliers. Okay, where AI, as usual, is the ith column of in this case, A transpose. Okay. Now, we were trying to show that we're optimal if we've got a positive, non-negative nu star. So we'll do our usual trick of we're taking, letting one of them be negative and trying to obtain a contradiction. So let's VI star be less than 0, e.g. we'll just use the first one, and let X star plus delta X be the optimizer of the EQP with the same set of active constraints, but with B1 replaced by B1 minus a small epsilon. Okay, so we're reducing the right hand side of one of our constraints by a small amount, and when we solve that problem, we'll get a perturbed x, which is x star plus delta x. Okay, so x star plus delta x is where x star moves to if constraint 1 were moved inward into our feasible region slightly. Okay. Note that if we reduce one of the right hand sides by a little bit, then the solution we'll get will be in the original feasible region. That's because the resulting x will satisfy the perturbed constraint and will therefore satisfy the original constraint as well, because it's going to be slightly less than b1. Okay, so we're going to maintain feasibility by doing this. So, as epsilon is greater than 0, x star plus delta x is feasible. And our Lagrange multiplier is less than 0, so our objective is equal to negative nu1 star delta b1. Okay, and delta b1 is just negative epsilon, so equals epsilon nu1 star. Okay, so what do we got here? We've seen that our Lagrange multiplier, our objective drops by, or changes by this amount here, which equals epsilon times nu1 star. But we've said that nu1 star is negative, so our objective is going to drop. Therefore, x star is not a minimizer of our overall problem, as we can move away from constraint 1 and slide along the other constraints. Reducing f in the process. Okay, so I think this is probably going to be easier to see. Well, nice to see if we sort of can represent this pictorially as well. Okay, so let's just see what this situation looks like in a picture. So let's say we've got a couple of constraints. Here we go, and we'll shade out as usual. So if we solve the EQP, let's just say our active set is these two constraints here. So call that one constraint number 1, and this one constraint number 2. Then this here is our x star. And this is constraint number 1, and with right hand side b1. Now if we decrease the right hand side, then what we're really doing is moving this constraint inwards. Whoa, let's try that again. So this is constraint 1 with right hand side b1 minus epsilon. Okay, so what I've done is what that does is it moves the constraint inwards into the feasible region. Okay, so f is the original feasible region. If I decrease my constraint, then what I'm doing is moving the constraint boundary into the feasible region. If we then recompute our optimum, This is the x star plus delta x that I was talking about. Okay? So that's the situation that we're dealing with in that previous problem. We're looking at whether it's possible, we're looking at what happens as we move this constraint boundary. Does our objective go up, or does our objective go down? So in the context of the original problem, what we're saying is that if the Lagrange multiplier is negative, it means we can move off along constraint 2 and lower our objective. So we can move away from constraint 1. So you can imagine that constraint 1 is moving, or just that it's static and we're moving away from it. We can move away from constraint 1, lowering our objective. So that's what it means for this Lagrange multipliers to all have to be positive. Okay. Alright, so with those ideas in mind, we can start to assemble the kind of nuts and bolts of a active set algorithm to solve an IQP. So we'll sort of present it to you in a sort of basic form to start with, and then we'll investigate how it works. So basic approach to an algorithm. Now you probably want to be happy with the previous part before you go on and watch this one, because we're basically going to use the idea that we just looked at before. And if you can sort of get your head around the geometry of what's going on as we move away from constraints, then it will help you to understand what's going on here. So always, to start an algorithm like this, we start at a feasible point, x0, and an initial active set. Okay, so that's our initialization step. Then what do we do? Well, this is what we'll do at each step. We calculate what I'll call x star EQP, which minimizes the EQP, which probably would x star and also nu star, sorry. Which minimizes the EQP defined by the current active set. Okay. We then have two possible outcomes. Okay, A. A first possibility is that the x star that we calculate is feasible. Okay, so it's possible that our optimizer x star may not even be feasible, so we need to allow for that as well. But first thing, if we're lucky, then our x star will be feasible. Okay, so we move to x star and check the Lagrange multipliers. Okay, if all of them are greater than 0, then we can stop. Okay, we're finished. Otherwise, if one of them is negative, like we just talked about before, if one of the constraints are negative, it means we can move away from that constraint and lower our objective. So we're going to remove one of the constraints with a negative Lagrange multiplier from the active set. Okay, so that's our step that we do if our X star is feasible, and it results in either finding optimality or removing S. Okay, so then we better look at the other case as well. So B, so the other case that might arise is that our X star EQP is infeasible. Okay, not so good. So what are we going to do here? Okay, so it's not an element of F. Well, we want to get to the X. We want to get to that point, but we can't. So we move as far as possible. Okay, because we know if we move towards X star EQP, our objective is going to be decreasing. So we move as far as we can in that direction until one of our constraints blocks us. So we move as far as possible along the line segment from X naught to X star EQP while staying feasible. Okay, and then we add to S the first constraint we encounter that blocks any further progress. Okay, so that's in essence the active set algorithm. Okay, shortly I'll give you the actual algorithm, and then in the next lecture we'll look at an example to make all these concepts a bit clearer. But essentially, once we've got an initial point and an initial active set, we start just following the same procedure. We optimize over our current active set. If it's optimal, we stop. Okay, if all the Lagrange multipliers are positive, we can stop. Otherwise, we just take out a constraint. If our X star is infeasible, then we move towards that optimum until we hit a constraint, and we add that to our active set. Okay, so once we've done either A or B, we've finished our iteration, and then we just go back and do it again until we're finished. Okay, so the problem of finding, so we know we need to find an initial X naught and an initial active set. So the problem of finding an initial feasible point is simply the problem of finding a feasible point. That satisfies AX less than or equal to B. Now that is something that we know how to do already. Okay? What we really have here is just a phase 1 problem. Whenever you're trying to find a feasible point, an X that satisfies a set of constraints, then we know that we can solve that as a phase 1 linear program. Okay, so don't get put off by the fact that we did it in our linear programming topic. The phase 1 problem is a linear program, and it will find us an X that satisfies the constraints. It will also tell us which constraints are active. Okay? This is simply the problem. Okay, so we know how to do this. This is the same feasibility problem we encountered in LP, and can be solved by solving a phase 1 LP. Hooray. Okay, so the initial active set is the set of constraints that are binding at x0. Okay, hold with equality. Okay, so we can use our linear programming techniques that we already know about to find ourselves an initial feasible point and an initial active set. Okay, so what I'm going to finish off with is I'm going to write down a slightly more formal version of the algorithm, one that will be easier to actually translate into computer code, and then I'll leave it at that for this lecture. In the next lecture we'll actually do a concrete example and I'll show you how the different parts of the algorithm are working as we go through it. So this one's the kind of meaty theory type lecture. The next one is going to be a much kind of more friendly example one. Okay, so the algorithm. So I've given you the basic idea of the algorithm. Now let's give you a slightly more correct algorithm. So 1. Let x equal x0 and s equal s0. Okay, so our initial x and our initial s. We're just initializing our variables s and x. 2. Let x star EQP and new star EQP solve the EQP defined by S. Okay, obviously we've got our problem defined and we just solve the EQP corresponding to the constraints in our active set. Okay, so we solve that. Then, if x star EQP is feasible, then we're going to do this. If our Lagrange multipliers are greater than or equal to 0, stop. X star EQP is optimal. Okay. In fact, if we want to lie this out a little bit more like code, I'd put that down here. Because I'm kind of indenting like you would in MATLAB. Otherwise, how about we make our code words blue as well? So I'll use the MATLAB syntax for if and else. Remove from S a constraint with a negative new star EQP entry. And then set x equals x star EQP and go to step 2. Okay, and we can even use our MATLAB end, how about that? Okay, so now we've got an else corresponding to our if from up here. So if we're not feasible, then let Tmax solve maximize T subject to x plus T x star EQP minus x is feasible. Okay, so what we're trying to do, so just note here, if t is 0, then this expression just gives us x. If t is 1, it gives us x star EQP. So this here gives us the line segment between x and x star EQP. And we're trying to go as far as we can while remaining feasible. So then we'll set x plus equal to x plus t max. Okay, so we're going to move to that point. Then we want to add to s, okay, new line, one constraint. That is binding at x plus. And that is violated by x star EQP. Okay, i.e. A transpose x star EQP is greater than b for that particular constraint. Okay, once we've done that, go to step 2. Okay, and then we can end. So basically, our algorithm skips between steps 2 and 3. We are solving an EQP, and then if it's feasible, we move to that point and get rid of a constraint, or we're done. Otherwise, we move to the boundary of the feasible region and add in a constraint, the one that we hit. Okay, so next lecture we're going to look at an example, and I'll show you graphically how this is working. But in the meantime, make sure you've got your head around the basic theory here, and I'll see you next lecture. Great, see you later.